So this is a past paper for diploma as well as advanced certificate, which they are now calling level 5 certificate in both automotive as well as heavy equipment repair, engineering science, meaning we're talking about first year. Since the paper was written in April 2025, of course, we're saying this is a revision package. Let's straight away look at question number 1. Question number 1, like I keep emphasizing, this is a compulsory question as usual. It says define the following derived units. Now, a derived unit is normally a combination of those ones we call the basic units. Examples, meters per second squared, kg per cubic meter, and the list goes on. Now, the base units, these are the ones that cannot be broken down into any further simpler units. They are basically like our building blocks. So, examples, we have things, units like seconds, kilograms, ampere, a candela for light, for illumination, and so forth. Then, sorry, let me remove this. Fundamental quantities. The same base units we talked about, to quantify them, you use base units, but what is it that you are quantifying? They are the fundamental quantities or simply the base quantities. Of course, these are units like length, mass, time, current, etc. Conversions, number 1, 20 kilometers per hour to meters per second. One thing you can see just by looking at this unit is that this unit that you see here is having kilo, and then there's also an hour here. A kilo represents 1,000 or 10 raised to the power 3. And then in 1 hour, because this one needs to be converted to that, in 1 hour, we have 60 minutes. Each of the 60 minutes has 60 seconds. So when you have to break down the number of seconds in 1 hour, you multiply by 60 minutes as well as by another 60, representing each of the 60 seconds held up in the minutes that are in those 60 minutes. So what are we saying? We're saying that converting such requires that you end up multiplying 60 by 60, which is like 3,600, of course. So that's why here you see 20, the kilo, it's 1,000. Then this is the breakdown we're talking about, 60 multiplied by 60. With that, your answer is 5.5 meters per second. Then we have the conversion now from 10 square centimeters to square millimeters. The first thing you may observe about these units is that pay attention to some of these small symbols written. Look at this. This is a square, another square there. The question didn't say convert from centimeter and then to millimeter. No. There's a square being added there as a power, which already tells us a story that we're not dealing with the actual conversions as they appear in our standard table of the prefixes that we know. So meaning that if I look at 1 square centimeter, in other words, what I'm saying is that in 1 centimeter, you have 10 millimeters. 1 centimeter actually represents 10 millimeters. But you can see here that the power is 1. With this time, what we've written here is 1 square centimeter. So meaning that this 10, the converting factor, is also supposed to be raised to the same power, which is 2. Let me repeat that. 1 square centimeter means that the converting number, which is 10, because we're saying 1 centimeter represents 10 millimeters. What about 1 square centimeter? It means that 10, the 10 millimeter is also going to be squared, just as the units are representing there. With this, now that you've laid down the language, we are saying this equivalent to that, then we can now bring down the question. What is our question? Our question is that we've been given 10, the 10 centimeters that we have here. And these 10 centimeters we have here, we are going to be very careful where we write them, because we can either write them on the right side, rather on the left side, or we decide to write them on the right-hand side. Naturally, we have to write them where the other square centimeters are. In this case, it's on the left. So here we are, 10 square centimeters written on the left, equivalent to x. Let me repeat that. The 10 is our question. This could have been any number that we are converting. That's why we've written it there. We are not going to subject it to this square, no. The one that we subject to this is the converting number, which appears in the standard table. Some of you may have used the centi. A cent represents 10 to the power negative 3. We apply the same rule. That same 10 to the power negative 3 has to be raised to power 2. For now, we use this other version. And at the end of the day, you still have the same answers. After this, we're just going to cross multiply. When you do the cross multiplication, we're simply saying that this 10, this 1 multiplied by, oh, rather, let me, sorry, get some other writer. This 1 multiplied by x, then this 10 multiplied by 10 squared. Now, in this, there's always that language of showing this, ensuring that you see how the units are disappearing. So here, we can therefore proceed now to do the cross multiplication, then we see what will happen after that. So here we are, 10 multiplied by 10 squared divided by 1 square centimeter. Already when you look at this, what you're going to have is like this. You're going to have this will go away, meaning this is what the units, this is what we're going to remain with. Now, the moment you've done this, it means you're just going to remain with the numbers. Which numbers are we having? We're having on top, it's 10 times 100 squared, 10 squared, which is like 10 multiplied by 100. The result is 1,000 square millimeters. The next question is asking us to find, or rather to prove that, or to prove this expression that has been given. The expression is, let me just read it again. It says, prove the dimensional correctness of the equation v is equal to square root of 2gh. In this one, I always tell people not to rush. The first thing you do is bring back the original SI unit so that nothing is going to be hidden from your view. And that being the first step, it means we are going to write this equation first. V is equal to square root of 2gh. Now, our question is, what are the units for V? What are the units for G? And what are the units for height, which is h? We can substitute them there. Let's start. V, which is velocity, is given by meter per second, meaning meter divided by second. We equate to the square root of 2 multiplied by G. G is given by meter per second squared, meaning meter divided by second squared. H is the height. So we're saying the height, the SI unit for height is meter. So these, if you want, you can even straight away say meter by meter, you have meter squared divided by second squared. So here we can do that, meter times meter, this is meter squared. The rest of the items, we are leaving them as they are. This is meter per second, so we've written it back the way it is. Then everything is under the root. Now, the next part is that these two numbers are multiplying. And one thing you can notice is that the power here is common. The power for the denominator and the power for the numerator, they're just the same. Meaning that you can put them in brackets and raise them to a single power. But perhaps before I even get there, let's introduce the dimensions so that we will end up on the right foot. Meter represents length. Second represents a dimension of time, which is t. So on the left, we are putting L over t. Then on the right, we have meter square, meaning that we are having L squared divided by second squared, which is like t squared. Now from there, you can already see what I said is that these are multiplying, so we can even separate them. Square root of 2 divided by, because these are having the same power, we can highlight them and leave the square outside the brackets. Now with this, it means that those powers we're talking about, this root, this power and this root, they will cancel. And therefore, you're going to remain with root 2, then L over T as our final expression. So L over T is equal to root 2, L over T, or L over T root 2. It's the same thing. Now, what's our conclusion? When you inspect, you notice that on the left-hand side, you're having L raised to power 1. On the right-hand side, you're also having L raised to power 1. It's on top. In other words, it's a numerator. On the left also, T is a denominator. It's below there. Then on the right, we also have this T, which is equal to a denominator raised to the same power. The only intruder making things look crazy is this root 2. Let's conclude. Square root of 2 does not represent any dimension. It's just a constant. Therefore, we can conclude that this equation is dimensionally correct. So that's our statement. Again, after you've done the working, please make your conclusion, make your statement to say, these are the findings. And you cannot make this conclusion before you prove with this working. Such kind of magic doesn't exist in science. You need to prove that, yes, this is how I've arrived at this conclusion, and then you leave it there. Question number 2, state the triangle forces law. This is a law where when three forces acting at a point in equilibrium, we are allowed to use those three forces, allow them to form the size of a triangle, and they'll be represented like that. So that's why we say that when those three forces acting at a point in equilibrium, we can represent, or they can be represented both in magnitude as well as in direction by the size of that triangle taken in what we are calling cyclic order, because they have to flow in some direction. All right, now state three effects of a force on an object. When an object is acted upon by a force, it can be deformed. Sometimes it can be caused to start moving, so it can cause motion. We can also damage that body, and so forth and so on. In some cases, depending on how that shape is, we can even cause a change in its dimensions, maybe it is compressed, and so forth. State two features or characteristics of a force. Naturally, a force is supposed to have the magnitude, direction, and of course, we know the SI unit is Newton, but the two characteristics are just magnitude and direction.